Everyone, my name is Ibrahim Azmi Safadi, and as an introduction for the flash separator design for methanol water mixture, first of all, a flash separator is also known as a flash drum. It's widely used in a process unit in chemical and petroleum industries that separates liquid mixtures into vapor and liquid phases by partial vaporization or condensation. This separation occurs due to a sudden reduction in pressure or increase in temperature, which causes the part of the feed to vaporize rapidly. The basic principle of a flash separator is based on a vapor-liquid equilibrium, VLE. When a liquid mixture is subjected to a pressure drop or a temperature increase, the more volatile components vaporize preferentially. The resulting vapor and liquid phases reach equilibrium and are separated mechanically within the vessel. The objective, first of all, we need to understand the feed conditions and thermodynamics assumptions necessary for flash separation for ideal solution. Secondly, to review and analyze the process conditions, temperature and pressure and composition typically used in flash separation processes for ideal liquid mixtures. Third of all, to assume and apply ideal solution behavior, enabling the use of route flow and Antoine equations in vapor-liquid equilibrium, VLE analysis. And lastly, to perform isothermal flash calculations for multi-component mixture, determining the number of moles in the vapor-liquid phases and the mole fractions of each component in both phases, liquid and vapor. Thank you.
Hi everyone, my name is Andrew. So the first step of the calculation is to state the assumptions and determine the overall compositions and the operating conditions. So the assumptions that have been made is that the mixture is an ideal solution and the basis is basically 1 mole of feed mixture. The operating conditions start with the pressure equals to 101.325 kilopascal, which is the atmospheric pressure, while the temperature is equal to 80 degrees Celsius, which is the temperature range between the normal boiling point of both methanol and water. The overall composition for the methanol, the Z1 is equal to 0.5 mole methanol per mole, while for the water is 0.5 mole water per mole.
So now we have to calculate the vapor pressure, which is Pset, using the Antoine equation. So in order to calculate the vapor pressure, we have to determine the parameters of each substances for Antoine equation from the table B.2. So after getting the parameters for the Antoine equation as shown in the slide, we can use them to calculate the vapor pressure using the Antoine equation as shown in the slide 2. So by substituting everything inside this equation, we can get that the P1 set is equal to 179.6685 kilopascal for the methanol, while P2 set is 47.4442 kilopascal for the water.
Calculating the vapor pressure for methanol and water using Antoine equation, and now we need to calculate the bubble point pressure and dew point pressure. And the formula used to calculate bubble point pressure is x1 P1 set plus x2 P2 set, and the bubble point pressure we got is 113.5563 kilopascal. On the other hand, we need to calculate the dew point pressure using the formula stated in the slide, and the dew point pressure we get is 75.066 kilopascal. Moving on to step 4, which is to calculate the K value, which is the equilibrium ratio. And K1 is equal to P1 set over total pressure, and K2 is equal to P2 set over total pressure. And the value we got for K1 is equal to 1.7732, whereas K2 is equal to 0.4682. Following up with step 5, which is to calculate the vapor phase and liquid phase mole fraction. Firstly, we need to calculate its x1, which is the liquid phase mole fraction for methanol, by using the formula P minus P2 set over P1 set minus P2 set. And the x1 we got is 0.4075 mole methanol per mole. Next, we can simply get the liquid phase mole fraction for water, x2, by simply using 1 minus x1. And the x2 we got is 0.5925 mole water per mole. After that, we can calculate the vapor phase mole fraction for methanol, y1, by using the formula y1 is equal to x1 k1, where the k1 is already calculated from the previous step. So after substituting all the values from the previous step that we calculated into the formula, we get y1 is equal to 0.7226 mole methanol per mole. And after that, we can get y2 by simply using the formula 1 minus y1. And we got 0.2774 mole water per mole for y2.
Hi everyone, I'm Woon. So after we calculate the mole fraction of vapor phase and liquid phase, now we can calculate the moles of vapor and liquid. So firstly, we can calculate V by using the formula the summation of Z times K divided by 1 plus V times K minus 1 equal to 1. And then we substitute the Z and K value for each component and solve the equation, and we will get V is equal to 0.2936 mole. After that, we can calculate L by using the formula 1 minus V, and we will get L is equal to 0.7064 mole. In conclusion, phase calculation is an important concept in designing the separation process of a mixture. It involves determining the amounts and compositions of the vapor and liquid phase at equilibrium that form when a binary or multi-component mixture is partially vaporized or condensed at given temperature and pressure. It can be applied to estimate the efficiency of phase separation and optimize product recovery. And here are the references that have been used in our project. That's all from us. Thank you.